looked at EAS reactions. We looked at halogenation, nitration, sulfonation. Are those the only three? Okay. We will look at others. Any questions about those thus far? EAS mechanism. In each of these reactions, you'll have to generate the electrophile and understand what the electrophile is. When you nitrate, the electrophile is what?
The nitrogen.
The what?
The nitrogen ion.
What's it called?
Nitronium.
Nitronium ion, yes. Okay. All right. At this point, we need to look at substituent effects. That is, if you nitrate benzene, you'll put a nitro group on, and every carbon is the same. You'll make nitrobenzene. How are we doing with nomenclature? Good. And by the way, there will be spectroscopy on test 2, just like on test 1. Comprehensive spec problems. There's problems in the workbook to be working. So spectroscopy and nomenclature there. Okay. What if we had chlorobenzene and we nitrated it? Where would the nitro group go? Because now the ring is no longer fully symmetrical and it can go adjacent to the chlorine. That would be called what? Ortho. Could go next would be meta and then or para. Okay? Nomenclature, right? Everybody's watched nomenclature? Good with ortho, meta, para? Okay. Activation, deactivation of rings. First topic, activation, deactivation. If you have an electron donating group on the ring, and I say net because a lot of times groups can be both donating and withdrawing. But if it's a net donator, this is going to be more reactive than benzene towards an EAS mechanism. Okay? If you have a net electron withdrawing group, this is going to be less reactive than benzene towards an EAS mechanism. Ultimately, electron donating groups lower the transition state energy for EAS by stabilizing the cationic intermediate. Electron withdrawing groups do not stabilize cation intermediates. Electron withdrawing groups destabilize. This illustrates that. If you have a net donating group on the ring, when the benzene ring attacks the electrophile transition state to give the sigma complex, resonance stabilized. Now we've got a donating group. And a donating group is going to stabilize the positive charge. Just inductively, we can see that. We'll also need to be able to do resonance structures with the donating group sometime. Since it stabilizes the positive charge, it makes the intermediate lower energy than here when there's no donating group. So things with donating groups, the intermediate is lower in energy. This is going to be faster reaction. It's going to be easier. Transition state energy is lowered. Now if we have a withdrawing group, that destabilizes the positive charge. That should be pretty clear just inductively. Pulling away from this area is not going to stabilize the positive charge. So it makes the sigma complex less stable compared to if there was no group there at all. Because this is less stable, the transition state energy leading to it is higher, and this is going to be a more difficult reaction. What we have to do is look at different types of groups. Which ones are net donators, which ones are net withdrawers. Various types of groups or substituents. I classify these according to 4 groups, I think. Group 1. Group 1 I call most books do this similar. Some books only have like 3 groups. I classify it as 4 groups. Same terminology. Group 1, strong activators, donators. This is going to be atoms with a lone pair other than halogen. Not halogen, though. Most common are going to be what? What atoms with lone pairs are most commonly seen bonded to a carbon? Oxygen and nitrogen. Could it be others? Yes. But not halogen. These atoms are more electronegative than carbon, both O and N especially. Thus they withdraw by induction, right? Isn't oxygen going to pull on a carbon? Yeah. Why am I calling them a strong donator, though? Since it's a strong donator, it is a strong activator. It makes the ring more active towards EAS. That's what that means. More reactive. Why? Because it's a strong donator. But I just told you it's a withdrawer. Well, that's by induction. However, their donation by resonance is very strong and is the predominant effect. So while the oxygen pulls by induction, its stronger effect is to donate by resonance. So what's the net effect? Donation. Okay? It's actually known to be a strong donator. Atoms with lone pairs other than halogen. There's 2 ways to show this. We could show it from a sigma complex with a charged species. We got cut off here a little bit. We can also show the resonance just from the starting material, starting compound. So here is a ring with an atom with a lone pair. Okay? Happens to be an ether. And what's the name of this compound, by the way? Okay, nomenclature video, yeah? Can we draw resonance structures here? Draw resonance structures there. What is your strategy for drawing resonance structures here? We said in organic 1, a conjugated lone pair is a great place to start drawing resonance, yeah? Okay, these electrons can move down here, and these electrons can move out here. Yeah? Yeah? And we can keep going. These electrons can move here, and these electrons can move out here. Yeah? And then these electrons can move here, and you can connect that as best you can there, yeah. And these electrons can move here. And then where can you go from there? These electrons went here, these would have to move up, and what would they do? It gives you back sort of the original, except the pi bonds in the ring are going to be moved. So the one on the end is a resonance structure of this, but we're back to the benzene ring. And the hybrid is going to look like what? The question is, which carbons of the ring have partial minus charge? By the way, the hybrid is going to look like that. Double bond character, single bond character, single bond character, single bond character. The true character is somewhere between single and double. The true character of every carbon-carbon bond in the ring is somewhere between single and double. What's the charge on the oxygen in the hybrid? Positive. What's the charge? Which atoms in the ring get negative? Related to the methoxy group. Which atoms? Ortho and para. The ortho and para positions are electron rich, we can say. Now I've done this from the neutral molecule. Again, I could have done it with a carbocation intermediate, and we would have stabilized the carbocation intermediate. Need to be able to do it both ways. This illustrates the electron donating properties of the oxygen atom by resonance into the ring. And hopefully you see that this is going to stabilize a carbocation that's going to form in the ring. Particularly group 2 are weak activators donators. And we'll see two types here. Conjugated pi bonds. These donate by resonance, a weak resonance donation. We'll also see alkyl groups. These donate by induction, which is typically weaker than resonance. So, both of these are weaker than group 1. This is going to be weak resonance. And since this is induction, it's inherently weaker than resonance. These are still donators. We can move electrons like this. These electrons can windshield wiper over. These can windshield wiper out. That would give this resonance structure, yeah? Carbocation here, anion in the ring. Now this is going to be a pretty minor resonance structure because we're generating a carbocation over here, no octet, but it's still a resonance structure. It might be better in this case to actually show a sigma complex. For example, if this pi bond attacked the bromine, okay, that's carbocation. How could the alkene stabilize the carbocation? Well, by resonance. So once you wiper it over and you've got resonance structure, yeah? So here I'm showing it both ways, from a neutral molecule, but also stabilizing a sigma complex.
Dr. Stevens, why does it do that, since that would be a primary carbocation and we don't ever, like,
That's not really a primary carbocation.
Okay.
It's resonance stabilized.
so it's different?
It's delocalized.
Okay.
And I did say it was very minor. And so the pi bond here can stabilize a positive charge, but this is going to be weaker than a lone pair stabilizing a positive charge. Alkyl groups donate by induction. Now, because this is just induction, this sp3 carbon, we're not able to show resonance structures. Okay, you don't show resonance with induction. But let's consider this attacking maybe an I+, and this attacking this way to leave carbocation here. And then we can show resonance structures of this. We can windshield wiper these down. Put carbocation there. Move these up. Put carbocation there. Yeah? Resonance structures of our sigma complex. Which one can we point to illustrate the inductive donation of the methyl group? Jamari?
Is it along the carbocation showing the resonance to the methyl group?
I didn't hear.
Is it along the carbocation showing the arrow to the carbocation on the methyl group at the top? And the first one in the blue?
This one? This one? And in what way?
It's showing resonance to stabilize that carbocation?
Resonance from the methyl?
I'm just saying resonance from the pi bond. It's showing the arrow movement stabilizing that carbocation where the methyl is.
You mean, this resonance here? What does that have to do with the methyl group? I mean, I can get rid of it and it's still resonance stabilized. Yep. We got a group on the ring. What is the group on the ring doing and where can you point to that at?
The group's donating its electrons.
What?
It's donating its electrons, that's why it's like positive.
It's donating its electrons, that's why it's positive?
Yeah, because it's like not fully, but it's like partially positive because of the resonance, and it's like donating its electrons to the ring.
You say it, you're talking about the methyl group is positive?
Well, it's not fully positive, it's like partially, because of the rate is pulling the electrons from the metal.
I reckon you could show partial charges with induction, usually you don't. I mean, I reckon you do, yeah. Okay, does everybody understand why the methyl group stabilizes it here? We really haven't said why or pointed it out. I'm trying to get you to point it out. Do what? I can't hear you.
Because it's tertiary, so it has
Yes, okay, great. It's tertiary here, right? You see? What's it here? Secondary? Secondary, it's tertiary. The methyl it's here. You say, hey, right here, this is an important resonance structure that we can point to, and because the methyl group being there makes that carbocation tertiary. So there's the effect of the methyl group. We see it in that resonance structure. And yes, this is I reckon you can show a dipole there. It's donating. I mean, I don't know how you're going to explain the effect of a methyl over here or here, but here I can hopefully explain the effect of the methyl. And if it wasn't there, you would not get stability. So the methyl group is stabilizing it. It's illustrated right there. But because that's induction, induction is not as strong as resonance. Group 3. Group 3 are weak deactivators, withdrawers. Most common here is halogen. So when halogen's on the ring, it's going to deactivate the ring. Deactivate the ring because they're withdrawers, net withdrawers. Like group 1 atoms, halogens both withdraw inductively and donate by resonance. Okay? You can do resonance with a halogen, just like we did with group 1 methoxy. And you can also withdraw. With halogens, which one's the greater effect, though? Withdrawing, because they're stronger, more electronegative. And it turns out that the withdrawing is the greater effect. Thus, they're net withdrawers, even though they can donate by resonance. So the inductive withdrawing is greater than the resonance donation. Group 4 are strong deactivators, withdrawers. These are going to be electron-poor atoms with no lone pair. And when I say atom, I'm talking about what's bonded to the ring. Okay? The atom bonded to the ring is going to be electron-poor with no lone pair. Examples are the nitro group. Little structure for nitro group coming off a ring. Isn't that it? Look at the nitrogen. Does it have a lone pair? No. Is it electron poor? Yes, it's a positive charge. Okay? You can also have a sulfone or a sulfonamide or something. The sulfur, no lone pair. Electron poor because it is bonded to these two oxygens. Carbonyls. Carbon has no lone pair. Electron poor because it's bonded to oxygen. Cyano group, no lone pair. Electron poor, bonded to nitrogen. Do these all look like they're electron poor atoms with no lone pair? Yeah, these are examples of that. What about a chlorine atom? Would that fit in here? No, chlorine has a lone pair. Anything with a lone pair can donate by resonance. As these groups have no lone pair, they can't donate by resonance. The only thing they can do is withdraw inductively. But because the atom that's bonded to the ring is pretty electron poor, they're strong withdrawers. Induction is strong. Inductive withdrawal is strong. Thus they're strong withdrawers / strong deactivators. They deactivate the ring. They make the ring less reactive. Towards what? Towards an EAS mechanism. You have to be careful when you say that something is less reactive. A number of you discussed this in lab report. You said the secondary alcohol was more reactive or something. But it was not clear. You didn't say more reactive towards what? And in many instances, I'm pretty sure you were not referring to oxidation. I think you were referring to carbocation stability. Secondary carbocation is more stable. Yet there's no carbocation formed in the oxidation reaction. So you have to be more clear with your discussion. And here, right now we're saying this is going to make the ring less reactive towards what type of reaction? EAS. Because in a couple more days, it's going to be just the opposite. We're going to say this makes the ring more reactive towards something else. You have to clarify what you're talking about when you say more reactive or less reactive. Because there's different types of reactivity. Okay, review in terms of reactivity. What's the name of this compound? We saw this in Organic 1 a good bit, I believe. Phenol, yeah. Phenol is more reactive towards what? EAS than toluene. Everybody agree? Why? What type of substituent is this? You can call it group whatever. Group 1. Why is it a strong activator? It's a lone pair, but it's not halogen. It's a lot of resonance. Okay? It's more reactive than toluene. Where does benzene fall here? If you just put benzene here, it would fall here. Why is toluene more reactive than benzene? Inductive effect. Right? Resonance, induction. Bromobenzene is less reactive than benzene. Why?
It's a halogen, so it's a withdrawing group.
You could start with that. It's group 3. It's a halogen. But then why? It can donate by resonance. But the stronger effect is Net electron withdrawing group. Yes, it can donate by resonance, but the net withdrawing is larger. Dual effects, which one is larger? And then something like this, why is this the least reactive of the four? You got an atom with no lone pair, and is this carbon going to donate? This atom had no lone pair, but that's an sp3 carbon, and we know that sp3 carbons donate inductively. Is that an sp3 carbon that's going to donate inductively? No, this is actually an electron poor carbon. Isn't there a partial positive on that carbon? Electron poor. And it's actually going to withdraw. You can actually draw resonance here the other way. I mean, we can move these electrons here. Yeah, resonance structure. Moving towards the electronegative oxygen, electrons flowing that way. I don't like the term flowing, they're just existing that way. But at this point, we can do additional resonance structures. And we start putting positive in the ring. And that's not good for EAS, because in EAS you form a positive in the ring. You don't stabilize a positive by removing electrons. We need donators to stabilize the positive. So an ester. So is an ester electron, is it an activator or a deactivator? So an ester is a deactivator? Okay, how about this ester? That's an ester, right?
So it depends then on where your carbonyl group is, right?
Uh-huh. What's bonding to the ring here?
Oxygen with lone pairs.
An atom with a lone pair? What group is that? That's group 1. So you just can't say an ester, it depends on how the ester's bonded. Now, not all group 1s are the same. Which oxygen can donate by resonance more? This or the lower one over there? This one. This can donate to the ring, but it's also donating which way? It's also donating the other way. You can draw resonance into the carbonyl. So while it's group 1, it's not as strong as this. On the next page, we'll kind of show some of that again. Before we get there, look at some example rates. Rate of nitration compared to benzene. Anybody figured out the name of this compound yet? We'll have to ask again later. Well, I'll just call it that compound. That compound reacts 10,000 times faster than benzene towards nitration. That's because the methoxy group is a group 1 strong activator. Toluene, the methyl group, is an activator, but it's a mild, weak activator. Because induction is a weaker effect. It reacts 25 times faster than benzene. Nitrobenzene, if you try to nitrate it a second time, the second nitration is 100,000 times slower than benzene. Why? Because the first nitro group is a strong deactivator. Deactivators make the reaction more difficult. Okay, these effects are additive. Which one of the following four is most reactive towards an EAS reaction? Well, just go through here. What do we have here? A weak activator? What is this?
A strong deactivator.
Strong deactivator. What is this? A weak deactivator. What is this? Strong activator. What is this? A weak deactivator. And this? Strong deactivator. Okay. Well, which one has the most activation? That's what we're looking for. It certainly ain't the one on the end. That's got... Which one's the most activated? Which one? Yes. What does this say over here? Most reactive of the following? What does it say? Which is?
There aren't any more words.
Well, this would be one. Can we rank these from what would be next? It may be a little bit difficult. Or which one is the most deactivated? Yeah. These two may be difficult. What do we got? A weak deactivator. Yeah, you see, you got sort of two extremes here, and then one that's kind of in between. So it's a little bit tough. I don't know. I sense that this, but that's really a strong deactivator. Those two are a little tough. Does everybody see why one is number one, though? And I think that's clearly the most deactivated. Okay? This is a listing from a textbook, probably the Smith textbook that we used a while back. And Smith grouped these a little bit differently. Strong activating, moderately activating, weak activating. Now see, the strong and moderate, I call group one. But see, the difference is, remember the ester that had the oxygen bonded, but it was to an ester? And I asked you, which one's going to be strongest activating, and we said the one just OH. Because here, the electrons are moving this way into the carbonyl. So that's why these are just called moderately activating as opposed to strong activating. But I just grouped these together as group one. And in group two, what were they? Like an alkene, but also just like a CH3 group or something, R group. Another aromatic would be sort of like an alkene, just pi bonds, carbon-carbon pi bonds. Group three, halogens. That's same, right? And the group four, lots of electron poor atoms with no lone pair. We said carbonyls, nitrile, sort of sulfonic acid. Pretty similar. Importantly, look at this. These are amino groups, okay? Group one, nitrogen with a lone pair. You got to be careful with the amino groups. If you're under acidic conditions, how will those exist? They will be protonated, and the nitrogen will be positive with no lone pair. And if it's positive with no lone pair, it becomes a strongly deactivating group. That is, if you're under acidic conditions, your amino groups are actually going to be deactivators. Because if they're protonated, right, if you protonate the amine, the lone pair is no longer there, and the nitrogen becomes positive. Okay? Either with acid or Lewis acid. Amines can become protonated or complex. Okay? Any questions about those groups? Now on the far right, it gives the directing effects, orthopara directing or meta directing. We'll move to that now. Second thing with substituents is directing effects. I'll continue to call this compound until someone can tell me the name of it.
Unisol.
Who said that?
No.
Yes, anisole. Anisole, if you nitrate it, you get a mixture. 45% orthonitro anisole. 55% paranitro anisole. And you get very negligible amount of metanitro anisole. Because you get a mixture of these two, predominantly, the methoxy group is called an orthopara director. It directs the new group either ortho or para. Not much direction at all meta. Okay?
That's because of where our partial negatives are at within the benzene ring, right? Due to
Well,
resonance?
yeah, we explained it by that. There's other ways to explain it, but that was one way. We saw where the methoxy donates, and it increases the electron density where?
In those
The
places.
ortho positions and the para. That was coming from the neutral molecule. We can also do that, we can also have an argument coming from the intermediate, where we stabilize the positive charge. Okay, here's our statement. Any atom that can donate somehow will be an orthopara director. Which groups donated? Groups 1 through 3. Right? If I agree that group 3 donated, how did group 3 donate? What was group 3? Halogens. Can a halogen donate?
Yes.
Yes. Is that its predominant effect?
No.
No. They can donate. Doesn't have to be the predominant effect. Groups 1 through 3 all donate. Those are all going to be orthopara directors. Group 4, which can only withdraw, is a meta director. For example, if you take nitrobenzene and nitrate it again, you'll predominantly get metanitration. You'll get a little bit of the other. But very often you can purify this out and just get sort of the meta product. And we call it predominantly a meta director. What about this here? What group is this? Group 4. What type of director? Orthopara or meta? Meta. If you brominate this with bromine and maybe iron precatalyst, the major product is going to be the meta-bromo product. All right? Down below, if you take bromobenzene and you iodinate it, iodine and an oxidant, what type of director is this? Orthopara or meta? Orthopara. You're going to get two major products. Okay? Now, ortho-para gives both as major products. You will have to purify these, and your yield may not be great. But very often, the para is sort of preferred. In theory, they're both preferred. Why might the para be preferred rather than the ortho? It has nothing to do with really the electronics of the group. It has to do more with
Stability? How more stable it would be if it were to be para instead of ortho?
why would it be more stable para? Well, really, the reaction depends on the transition state energy. So that's really what we want to look at. It doesn't matter what the end result is. It's transition state energy that drives the outcome. It has to do with sterics, okay? For the group to approach up there near that other group, okay? This has to be up here when it reacts, right? Electrophile has to be up here when this reacts. Well, these bumping around with each other, they're going to want to avoid each other a little bit, yeah? Okay? So sometimes you may get a little bit more para. You know, up here you actually got more para. Okay, orthopara. Actually, you got way more than this. You had twice the chance of getting nitros ortho, but it still only gave 45%. So you can say you got like 22% at each site. But at this site, you got 55%. There's only one pair of carbon. There's two ortho carbons. If the reactivity was the same for all, shouldn't you get like twice as much as this? You got two carbons, right? I mean, if we had nitrated over there, it'd be the same product. So you kind of see that you're getting more para up there. But still, the ortho is going to be pretty substantial. We call it ortho-para director. We need to look at resonance structures to understand the directing effects, okay? Please look at those. We've already done a little bit of resonance structures. That'll be a little bit more. Need to be able to draw resonance structures here. All right. You learn how to draw resonance in organic 1? Same thing. Nothing new. We're just using it, doing it. Have a good day, guys. Friedel Crafts, blue handout on Wednesday.